There we go. We'll share again. All right. Now I've lost my chat window. Oh, wait. There it is. All right. All right, so let me see. Erdős, so itinerant, he traveled around from place to place. It is reported that he had a battered old suitcase. I think that was leather, but he also carried around what was essentially an IKEA bag, one of those kind of knit plastic bags. They were more popular in Europe before they were popular here. Um, so from some retailer in Europe, and he carried his belongings in these bags, and he would just show up at a mathematician's home, somebody that he knew that he had met by virtue of another mathematician or whatever, but he would show up at their house. It could be any time of the day or night. And when you opened the door, he would say, "I have an open brain." And he would stay for a day or two or a week or two. And then at some point, he would just leave. And when he was there, he was a frenzy of mathematical thought. He asked problems. That's really where Erdős gets his reputation. He had questions about everything, and he had ideas. He wasn't much of a closer, it seems like, in terms of these sorts of things. So he would kind of, you put in the details. But he would show up and he would talk to you and work day and night. He hardly slept. He was addicted to caffeine and a number of other substances. I believe, I believe it was cocaine. Really, honestly, he reminds me of a mathematical Sherlock Holmes. All intuition, lots of ticks, not necessarily the nicest person or the best friend or anything, but brilliant. And in his case, I believe it was cocaine. Forgive me if I've got the drug wrong, but that seems appropriate for his lifestyle. And there may have been some other things involved, but he is one of the most prolific authors, therefore, of the last century, mathematically, of course. I can't remember now how many papers, but it was dozens of papers per year, multiple dozens, not just a dozen per year. He published more papers most years than most mathematicians published in a lifetime. And some of that, of course, was, he had a lot of collaborators who would work with him. One of his best known collaborators, and my candidate for a guy that in math who I would most like to have a beer with, is Ron Graham. Ron Graham works, I believe, at Stanford currently. I have an Erdős number of infinity. I have not published a paper yet. I am procrastinating publishing my papers that came out of my dissertation still. And I know I have too much fun teaching and asking the questions, and not enough. I'm not much of a closer either, let me be honest. So in terms of Erdish's lifestyle, he and I have almost nothing in common. I'm a family man. I am not a drug addict. Maybe caffeine, but one thing that I can totally relate to is I get distracted easily. So before I finish writing something up, I get distracted. I'd like to think so. Um, I'd like to think there's some merit to that, but before I finish writing something up, I usually get distracted by another problem, or sometimes I just get distracted by real life. That's not something mathematicians, like hardcore mathematicians, can usually afford to be, is distracted by real life. I mean, Andrew Wiles locked himself in his attic for 5 years. Yeah, I've heard about that. I'm trying to avoid it, actually. I try and avoid all those sorts of things. Um, but sure. Um, so yeah, I can relate to Erdish's uh, desire to move on to the next problem once the previous one seems pretty well settled. Um, Regardless of the fact that you've not bothered to actually write it down or submit it to a journal or anything like that. And honestly, that's part of what allowed him, probably anyway, to publish so many papers. Is he would publish 50 papers in a year, but he was not submitting them to journals. And once he had published his first 50 or so papers, having his name on it was pretty well a surefire way to get a paper accepted by a journal. I mean, they weren't likely to say, "Oh, this Erdish guy doesn't know what he's talking about." So there's a lot to that. When Erdish died, he left a battery of questions, and you can Google for them and find them. I actually, there's a graph theory one that's completely accessible to us, and I sometimes share it, but I don't have it handy today. So maybe I'll pull that up on Wednesday or some other day and show you guys. Uh, Everything about the statement of the problem is completely understandable as soon as we had talked about most of chapter 3. It is not a difficult problem to understand, but it's an unsolved problem. And so these Erdish problems, as they're sometimes called, they all have prize money attached to them, because that's another thing he would do. Is he would work on a problem for a minute, and then he would decide he didn't want to solve it, and he would say something like, "I think that's a $5 problem," or "I think that's a $50 problem," or occasionally, a $500 problem or something like that. And he would actually, if somebody solved the problem, offer them this money, and then he would probably publish a paper with them since he posed to the problem. And it was, by this time, an honor to publish a paper with him. So even though you did all the work, you didn't mind having his name as a co-author. It got you an Erdish number of 1 and a guaranteed in a journal, most likely. Ron Graham is actually the curator of the Erdish problems. And if you solve an open Erdish problem, you get to choose now, because Erdish is dead and his bank account was never super full to begin with. You get to choose. He wrote out a number of checks before he died to cover these. So you get to choose between a check from Erdish that you can't cash, or a check from Ron Graham, which you can cash. And in my mind, this means that if I ever solve an Erdish problem, I have to solve 2, because I want both. I'm not going to cash either one of them. I mean, I think Ron Graham is kind of a modern day math hero too. He doesn't get quite the press that Erdish got, but this guy he has his hands in a lot of modern mathematics from the last 20 or 30 years. So I think he's somebody that people are going to remember past his own century. Ron was worried about his friend. Paul Erdős, and especially his drug habit. And he once bet him $500 that he couldn't go a month without his, and again, I can't remember if it's cocaine or amphetamines or whatever it was. I think it was cocaine though. And Erdős did it. He went a month without to win the bet, collected the money, said it was the worst, least productive month of his life, and then immediately went back to drug use. I'm not advocating drug use, just saying this is, the kind of character he was, and the kind of character Ron Graham is. Like I said, that's one of the things that makes me think he might be a nice guy to have a beer with if he was willing to try to challenge his friend in that way, in a friendly sort of way that might have actually worked if Erdős hadn't been so bullheaded. So Ron Graham, it might have been, it was probably more than one thing by the end of his life. Like, it wouldn't surprise me if something like cocaine was kind of his gateway, but at some point I'm sure he was doing more than just that, because that's the nature of drug abuse, right? Speaking of mathematicians that are remembered beyond their century, this is just a little bit of my philosophy on how mathematics works. So people ask me why I do things, and why I do things like Ramsey theory, why I care about that. And the honest to goodness truth is I do it because it's pretty and it's interesting. I technically have degrees in applied mathematics, but I don't do mathematics because of the applications, not typically. I typically work through mathematics. I typically work through mathematics that I find beautiful or interesting. And I love this quote from Hardy. It's a little bit more respectful from the one that I normally give my Calc 3 students. I love that he says that it's distinctly more useful than applied. And it's true here. The technique in pure mathematics that's the point of it. You're learning how to think. There are some people that would even suggest that by studying proof in pure mathematics that you're learning to think more like the divine. That might be a little bit too much hubris, but that's the kind of approach that you take. My favorite way of expressing this is that Hardy is quoted as saying, "I have never in my life done anything useful." So the same notion. And the irony of Hardy is just, I love the irony of Hardy. He was not atheist exactly. I mean, that's what he would have said. I believe that word was invented at the time, but he was more anti-theist. He believed that God hated him, probably because he didn't believe in God. And I understand there's a little bit of contradiction there, but it's the kind of contradiction that was, perfectly acceptable for Hardy. He would go to a cricket match, and he would take papers to read and work and an umbrella and all of these things, because he would try to trick God into thinking that he really hoped that the match would get rained out so that he could get some work done, so that the match wouldn't get rained out and he could enjoy the cricket match. He once was getting on a ship for a voyage. It was a fairly long voyage, and he was not convinced that he was going to live. So he wrote to one of his colleagues that he had discovered a proof for the Riemann hypothesis, I believe it was. It was either the Riemann hypothesis or Fermat's last theorem, and that he'd share it with him when he got back. because then he believed that if God killed him on the way, that God wouldn't kill him on the way because he would die with people believing that he had done this great thing, so God would let him live. That's what I mean when I say sort of an anti-theist. He's a really weird, interesting character. Mathematics is filled with them. I will admit that mathematics comes with a higher than normal correlation to left-handedness. And it also comes with a higher than normal correlation to mental illness, as you might not be surprised to learn. So all of that said, I want to actually talk to you about a completely different mathematician, and his name is Stirling. And you guys know a little bit about his work because we've talked about it. You guys have seen all of this. Like I said, this talk was given for somebody that didn't have a basics of combinatorics. So falling factorials, I didn't even tell them about the rising factorials. I was, trimming things down. Chromatic polynomial, you guys have seen the chromatic polynomial. Just a reminder down here that, that the mouse does not highlight when I'm in PowerPoint mode. That was a reminder for me. The reminder for you is that the chromatic number of the complete graph on n nodes is the falling factorial. So just these are some things that we're going to put together here in a second. You guys have seen at least some of these formulas. You know we didn't talk about the Stirling numbers, the first kind, in class. Technically, the one I've given here, where you put it in kind of binomial coefficient mode, is the unsigned Stirling number of the first kind. That's not what the title of the page says, but that's what it is. If you give it a sign, if you give it a minus, I think it's that -1 to the n minus k down below. It might just be -1 to the k though. You get the signed Stirling numbers. Basically, sometimes that negative sign shows up and sometimes it doesn't, and so people can't decide which one is the go-to version. I like the unsigned numbers because it has a nice combinatorial meaning, the number of permutations of an inset with k distinct cycles. That's the one that we've been using, and I don't mind throwing in the -1 correcting factor if I'm in a formula or something. I think that's the way I prefer it, but nobody asks me. So the bottom formula on this page we've had for quite some time in our class. It's the one that I can never remember, and so I always look it up, but it's also the one that we derived. We actually derived it for the k factorial, s of n comma k. By the way, the curly brace and the square brace are my preferred notation. Earlier in the class, I used the cap s because that was the notation in our book. We've kind of moved beyond our book now, so I'm going to use this notation. These things, to me, behave more like binomial coefficients than they do anything else. And I prefer the binomial coefficient notation for the choose function as well. So I think I'm consistent at least. So none of this on the last few slides was new information for you guys, except possibly, yeah, absolutely, I can do that. I'll post it right after class. So, oh, it's 10:55. Oh my goodness. Well, I guess today you just get the history lesson and you don't get the upshot because I need to let you guys go, don't I? Sorry about that. I had you cover in my clock or else I'd have stopped a couple of slides back. We'll go ahead and pick this up on Wednesday, and I will go ahead and post the rest of the presentation. That formula in the middle of this page, though, is kind of an interesting one, and you might want to take a look at that. Anyway, I'll see you guys on Wednesday, all right? Yeah, you guys too.